So take this situation where you're stranded in the middle of nowhere. This is my middle of nowhere with my cactus, right? And you're just dying, but you do have a phone. Unfortunately, that phone is on no battery. Or actually, you know what? Let's be kind. Let's say you have some battery. Your battery's in the red. You look around you, and you luckily have some copper and some zinc. Okay, so you have some copper and some zinc. And then, of course, you for some reason have the sulfate versions of both of those. What do you do? What can you do? Well, what you can do is you can make a battery to charge your phone's battery and get you back up to that green. Okay, but how do you do this? What in the world? Well, for that, you do have to grasp some very basic fundamentals of electrochemistry. So let's get into that. First off, what is electrochemistry, right? Electrochemistry is basically oops, sorry, that's a little messy. Electrochemistry is the study of the chemistry, I guess, of electricity, and how specifically how electricity is generated and created and all of that. Okay, so let's go over a couple things. So when we do have the battery, right? When we do have that battery, this is called a galvanic cell. I wish I could spell today. Galvanic, or voltaic is also called voltaic cell. And what this does is it just outputs energy, and it basically only outputs energy. This is in stark contrast to a reverse reaction, which is called the electrolytic cell. And this one is basically stores / takes in energy. So taking our basic phone battery, so this is our phone battery, for example. When we're using it on day-to-day use, it's a galvanic cell because it's leaving. And then when we charge it, it basically becomes a electrolytic cell. Okay, so there are different types of batteries, there are different types of cells. Why does that matter? Because we make batteries, right? Without it, you couldn't Snapchat your mom. So let's figure out how to draw a galvanic cell, because it does have a couple parts to it. There are actually 4 main components to it. So we have an anode. Oh, not 4. So it'd be weird to start with 4, wouldn't it? We have an anode. We have a cathode. We have a salt bridge. And then we have a wire or mesh or something that takes out electrons. If you'll take a quick look and notice, it says anode and cathode, right? Where have we seen those before? Well, we have seen an anion and cation, right? And it's no coincidence. What's a cross? I think purple's a cross on the color wheel, green on the color wheel. And it's no coincidence that anode and cathode start with anion and cation. Basically, what happens is anions are attracted to anodes, and cations are attracted to cathodes. So that since we know that anions are negatively charged and cations are positively charged, we must know that the anode is positively charged and the cathode is negatively charged. Okay, so we know charges. Why is that significant? Because we can figure out which node is being oxidized and reduced Yeah, we're back on good old favorite redox. Let's refer back to our good friend Leo the Lion. Leo the Lion goes grr. Leo the Lion goes grr. What does it mean? It means losing electrons is oxidizing. So becoming more positive is oxidizing. And grr is gain electrons reduced or becoming more negative. Okay, so from here we can figure out that anode is the site of oxidation and the cathode is the site of reduction. Super simple. Okay, that's shockingly uncomplicated. Okay, so let's draw those. I'll zoom out a little. Actually, no. Let's define everything first, and then let's draw them. Right. So next we have a salt bridge. What that is literally a bridge between our two cells with just full of a salt. It often doesn't react, and all it does is it just neutralizes because our anode and cathode both become so ionized, both become very positive and negative. Our salt bridge, what happens is that's what gives off the anions and cations to go and neutralize basically our battery, or either side of our battery, and that's super important to do because if the batteries get ionized, if they get super positive and super negative, what will happen is the battery will just stop working, and yeah, dead phone. No one likes a dead phone. And then the wire is just what we use to take out our electricity, and the electron will always move from the anode to the cathode, and the electron is what gives us power. I don't know why that I was squiggly. That's what gives us power. Okay, so now that we have all of our definitions down, let's draw a galvanic cell. No, you're gonna have to be able to do this. So what I'm gonna do is I'm gonna label the anode as green. Oh, I already used green. Sorry. I'll use red and blue this time. I'm gonna label the anode as blue and our cathode as red. Okay, so on the right, almost always you'll see on the right that we have this anode. It's gonna be a little container with our metal in it, and then on the opposite side, on the left is gonna be our anode, and then on our right, sorry, I should really know my left and my right, shouldn't I? On the right is gonna be our cathode. Here's the cathode. Okay, and then we're gonna have our wire connecting it. Here's our voltmeter, voltometer, whatever you want to pronounce it. It just measures out the how many volts we're creating, and the electrons are gonna be going this way. Okay, and then basically, and then we're gonna surrounding the liquid is gonna be a little bit of solution of just a liquid in ionized form. Oh, actually, I like that. I should have kept that, but oh well. If you ever really get confused, oh, and I almost forgot to put it in, but we have to remember the salt bridge. This looks like salt. We do have to remember the salt bridge. And yeah. Okay, so if you ever do happen to get confused on like, oh, what's the anode, what's the cathode, I've come up with a nonsensical mnemonic. It's Leo goes gurk. Or sometimes the way I remember it is Aaliyah, but just keep it straight in your head that Aaliyah, it's going to be oxidizing regardless, right? I came up with this mnemonic just by sticking anode and cathode on either end of the spectrum. Just to kind of remind myself that the anodes will almost always go on the left and the cathode will almost always be on the right. However you want to do it, really, it's fine. Just remember it. That's the only important part. Okay. So, that's basically everything. Oh, and just a little quick note. Inside the salt bridge is going to be like NaCl. It's going to be like lithium hydroxide. It's not going to be lithium hydroxide is a 1. It's definitely not going to be like Ag or something that could oxidize really easily, or something that will react really easily, right? Okay. One more thing that I should mention that I think is pretty important to mention is there is a shorthand. So in case you didn't want to draw that, that whole monstrosity that took up this much of my screen, what you could do is there is a shorthand where it goes anode with a little line, one line I mean, and then the anode in solution. I completely butchered its spelling, but I swear it says anode in solution with the concentration in molarity, and then a double line, cathode solution, once again in molarity, single line, cathode. The single lines mean that there is a phase change. I'm gonna put delta phase. Right? And then this double line is gonna mean that there's an actual barrier. It can also mean salt bridge, but yeah, barrier and salt bridge are basically the same idea. Okay, so just remember that I went over really fast, but just kind of keep that in mind. It might be important to know if you're taking like the MCAT or something like that. It might be important there. Okay, so we drew our voltaic cell earlier. And now we have to figure out what our electrolytic cell will look like. And the good news is you basically just the only thing that switches is the anion and the cation, right? So the anode and cathode, I should say, actually. It's just all it does is that now we C and A like that, and we have everything else the same with our salt bridge and our wire connecting something, and we have this guy and the metal and in solution, right? I think a quick thing to note is that the anode is always the side of oxidation, oxidize, and then conversely the cathode is always the side of reduction. Okay, so not too bad. Sometimes you will see like if we're like if we're making sodium metal from salt, sometimes you will see that they will be in just one thing with molten sodium, and then we'll have some electricity going into it, and we have either node, and we have some electricity going into it, and then you'll see like chlorine bubbles coming out, and then some molten sodium forming, right? Sometimes it will be in one container. You really won't see a galvanic cell in one container unless they're like separated with like barriers or something like that. But yeah, that's really all. Now let's move on to figuring out if we would make a good galvanic cell or a good electrolytic cell, right? Because I feel like we have to know how to use batteries and how to make batteries in case we're ever stuck in the desert. Remember from thermo that we do have spontaneous versus non-spontaneous reactions, meaning this one will happen and this one won't, right? And so our galvanic cell is spontaneous because it just happens, right? We don't have to shove electricity into it. And conversely, because we're shoving a bunch of electricity into it, our electrolytic cell will be non-spontaneous, right? Therefore, our galvanic cell must have a negative delta G for Gibbs free energy and positive delta G for our electrolytic cell. But I don't know about you, but like, what is a Gibbs free energy? I have no clue what it is. I mean, I know it's a way to measure energy and a change of energy and whatnot, but who is Gibb? What is Gibb? gib. So instead, most of us, we consider electricity in volts, right? Shocker. Haha, get that pun? Man, I wish I could draw. Volts. That's a lightning bolt, I swear. Boom, it's a lightning bolt. And so the way the way we have to think about it is positive E cell. This means cell potential. Positive E cell. E means EMF, or electromotive force, meaning how much we go, how much our electricity goes, right? And negative E cell for our non-spontaneous. Okay, so how do we calculate any of this? What's going to happen is basically we're going to have to use basically Hess's law. Hess's law is a chemist's favorite rule, maybe right after Puvnert. Puvnert is great. So let's consider this cell. Zinc plus 2, 1 molar. Ooh, I feel like I might have to sneeze. I'm so sorry if I blow out your eardrums. 1 molar. I can cut it out. What am I saying? Yeah. Okay. So we have all of this. Remember that this side is the anodes, and remember that this side is the cathodes, right? So what we're gonna do is, oh, sorry for the noise. There's lots of people outside. So we're gonna have that. Well, we need to know what's being reduced, what's being oxidized, right? And we have anode, cathode, a Leo, Gurk. You can do that, or you can do whatever other mnemonics are better. I heard something about a redox, but I have no clue. So once we do split them up, what's going to happen is we're going to have zinc plus 2E minus, and copper plus 2E minus becomes copper, right? And then we have to look up on our reduction potentials table, right? Our reductions potentials table. And do remember that it says reduction potential, so it's going to be reducing. Yeah, whichever one's being oxidized, in this case our zinc, its reduction potential is going to have to be flipped. Right, okay, so then we're just going to, 1.102, and then that's going to be, so then we're going to add up the two reduction potentials. This one's going to be obviously flipped. The sign's going to be flipped, I should say, and that's going to lead to an E cell of 1.102. Therefore, our zinc copper battery is going to be spontaneous, and it's going to be a galvanic cell. I feel like I just dumped a whole load of information on you, so let's kind of clean this up a little, right? Next week we'll go into more things like the Nernst equation, Faraday, and all of that. But for today, I feel like just kind of dip our toes in, get it ready to deal with it. So let's consider the battery formed by zinc and silver. Okay, well let's first let's draw let's draw what the cell is going to look like, and let's draw let's figure out what's being oxidized, what's being reduced. So let's first very first thing, we need to figure out what's being oxidized, what's being reduced. You can do this in a plethora of ways. I'm just gonna assign oxidation numbers. I think that's the easiest. So we're gonna have 0, 1, 2, 0. Okay, and then we go Leo. Oops, it's not EO, it's Leo, and Leo goes Gur. Okay, so what's becoming more positive, what's becoming more negative, right? We have O, the O being oxidized, sorry. Oxidized is our zinc, so zinc is going to zinc plus 2E minus, and reduced is our silver, it's going Ag plus E minus becomes Ag. Okay, so we have what's being reduced, what's being oxidized. Then we can consider a Leo goes Gurk, or whatever else you want. I don't really mind. And then we're going to know that we have an anode here, and then a cathode right here. Okay, perfect, perfect. Then we're going to have some metal right here like this, another bit of metal like this, connected via wire to, let's say, another voltmeter. And we're going to have our salt bridge. Do not forget the salt bridge, ever, 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 because you want functioning batteries. You know what, this is becoming a monochromatic nightmare. Man, that was a hard thing to say. It's because it's becoming a monochromatic nightmare. Let's use purple and green, the Hulk. So this is our anode. This is our cathode. I don't know why I changed it up. Anode, cathode, anode's liquid, cathode's liquid, and this is the salt. The rainbow is salt. And then oh, that's an actual rainbow, come on. The wire is copper, so it's green, obviously. Right, and then we can have the voltmeter in the middle there. And oh man, now it's a Technicolor nightmare. Yeah. So, and then, you know, we're going to have some random chemical in here. I'm just going to say potassium hydroxide's in here. So KOH is going to be in here. So it's going to be K plus OH minus, right? One's an anode, or one's an anion, one's a cation. The anions, the OH, the OH, the anion, is going to travel, towards the anode. The cation is going to, oh, I just left my K. And the cation is going to travel towards the cathode. Just to kind of visualize what happens. Next, so we have our battery drawn. Now we have to figure out, is it galvanic, is it voltaic? Or not voltaic, is it galvanic or is it electrolytic? Remember, galvanic and voltaic mean the same thing. So luckily we have our half equations already right here. So we kind of lucked out. We already did most of the work for ourselves. We just move this guy. Sorry, let me just move him a little further this way. And then we consult our big table of reduction potentials, and we find that this guy has an E red of minus 0.76 and an E red of 0.8. Remember, because this guy is being oxidized, we have to flip the sign, like basically Hess's law. So it's, why did I just add 1 to it? Plus 6. And then we can do, and then to find E cell equals E red plus E red is equals 0.76 plus 0.8 equals 1.56. Because we have a positive cell potential, we know that this zinc silver battery is going to be a galvanic cell. Basically, what that means is we're going to have our electrons going from the anode and going towards the cathode. And just something interesting that I thought I would mention is that we're actually going to see our anode start to disappear like that. So it's actually going to start to like disappear like that, and then our cathode is going to start just gaining mass. Yeah. Anyways, I thought that was kind of interesting. You don't have to. Anyways, I do hope that was helpful, and good luck.